So I'm Tom. I'm going to be talking about how code compilation works. So why does understanding compilers matter? Compilers are tools which most of us will have used. A competent computing professional understands high-level programming languages, and they understand hardware. And a compiler is what links the two together. Therefore, it's imperative to understand compilation techniques to understand how programming languages and computers hang. It's good to understand how the tools we use work, and it allows us to consider attack vectors which we otherwise wouldn't have known of. So, the compiler pipeline. This is kind of a simplified pipeline that your code will go through the compiler. There's lexing, parsing, semantic analysis, optimization, and code generation. And I'm going to give a brief overview of each now. So, lexing. There's cool animations, by the way. I was up at like 5 a.m. doing this. So, lexing, also known as tokenizing or scanning, is where you effectively give meaning to the characters in the source code. So, if we take the line var a equals var b plus 100 as an example, the lexer will break this down into characters. It will then group those characters, strip any unnecessary white space, and assign kind of meaning to those characters. So like var a and var b identifiers, equals and plus are symbols, 100 is an integer. And then these tokens, known as lexemes, are passed into the parser. So the parser takes the lexemes that were spit out by the lexer. It then kind of enforces a structure to them. It creates what's called an abstract syntax tree, where you have kind of a hierarchy of operations. So in this case, the equals operator takes two parameters almost. There's var a, and then there's the result of the plus assignment, which is var b plus 100. So it kind of enforces a rigid structure to the lexemes that it takes. With parsing, you can think of it as taking the tokens and extracting almost what you want to do with them. So rather than think of them as just an array of tokens, you think of it as you want to add 100 to var b, and then you assign that to var a, as is shown in the abstract syntax tree. We'll go on more on how this works later on. The next step is semantic analysis. Semantic analysis is like there is a lot to it. Too much to cover in half an hour. But two of the main things that happens during semantic analysis is what's called type checking and name binding. Semantic analysis is just where you take the structure, the syntax trees that the parser spits out, and verify that they make sense semantically. So for example, with regular language, if you had the sentence colorless green egg green green, that would not pass the parser. That structurally doesn't make sense. So the parser would spit out a syntax error and say that doesn't make sense. If you had the sentence colorless green, that passes the parser. Structurally it makes sense, but semantically it doesn't make sense. Semantic analysis is where that kind of error would be caught. So type checking, it's the process of verifying and enforcing types within code. So if you were to have var a is equal to a string, and you try adding 102 to that string, any reasonable language is going to throw a type error, because you can't add an integer to a string that doesn't make sense. Same as if you have a function where you pass in a character and you try passing in a float instead. That's also a type error. The other thing that type checking also does is what's called type inferences, which is where type is inferred based on whatever it's being assigned to. So if we had var b is equal to the result of function b, the type of var b is determined by the value of function, the return value of function b. At this point, we don't know what the return value of function b is, but that's where name binding comes in. Name binding associates kind of labels, names to data, code, etc. There's two types of name binding. The static binding, which is like calling directly calling a function in C, for example, where during compile time, that identifier is bound to wherever the function in memory is. You know during compile time where that's going to be, and so you can do it during compile time. Dynamic binding takes place during runtime. In an object-oriented language like C++, this would be like the dynamic dispatch, where you don't necessarily know where the function is going to be, so you have to work that out during compile time. But obviously, dynamic binding doesn't really take place in the compiler. It was just important to kind of make the differentiation there. So PowerPoint errors were really annoying, but this is the best I could do at 5 a.m. So if we have int func b, we know that func b now returns an integer. Name binding will associate kind of label func b to that bit of memory and will assign that return type to the function. Then string is b5. So looking at var b, now we know that func b returns an integer. We can now go back to type checking and verify that yes, var b is an integer. Then when we try comparing var b to an integer, the compiler is happy because we're comparing an integer to an integer and that's allowed. One other thing that happens during semantic analysis is the compiler will go down every path that the function can take and every return value that is that's possible. So in this case, there's two possible return values, yes and no, which are both strings, and the return value of is b5 is a string. So again, the compiler is happy because the function always returns a string. If, for example, there was a case where it didn't return a string, then semantic analysis would throw an error. So optimization. Optimization is also really broad. There's a lot that happens in optimization. But again, there are two kind of main optimizations which take place and make up the majority of the performance increase in through optimization, which is inlining and partial evaluation. Inlining is just putting functions in functions. So if we take this code, for example, we have the function func. There's an if statement where it either returns a very, very long function or it returns b, and b is just returning a string. The way inlining would work is, once it has been inlined, the function b will be removed, and every instance of calling function b will be replaced with the code in function b. This obviously means there's less function calls, which is good because less instructions to run, more efficient. It does have the drawback of increasing the size of the resulting executable, and partly for that reason, this only really happens with small functions. And another reason why you don't inline large functions, in this case very, very long function, is because of what's called cache misses. So when the CPU is running code, the next chunk of assembly will be loaded into memory, into the cache, so that it can be quickly executed. If you go into this if statement and you've loaded in very, very long function, and you're not going into very, very long function, so you have to skip to function b, then you're having to retrieve that from memory. It's not in the cache. You incur a cache miss, and that has a performance hit. There are obviously cases where it would make sense to inline a large function. And in languages like C and C++, you can specify the inline keyword when you're defining a function, which tells the compiler that you should probably inline this if possible. The inline keyword doesn't necessarily mean that the compiler will inline the function, but it makes it much more likely. And you can kind of tell the compiler that you want to make this inline to make your code more efficient. If you know, for example, you don't really care about the drawback of it being larger, or you know that you're not really going to incur many cache misses by doing it. Partial evaluation is just propagating known information. So going back into this, if we assume var_c doesn't change between it being set to false and func being run, then we know that the if statement is never going to return into the very, very long function. So we can just get rid of the if statement and just return b. And then if we apply inlining as well, we get rid of B and just put that into func C, and we get rid of a huge chunk of code. Again, you can almost speak to the compiler about partial evaluation. In languages like C and C++, you can mark a variable as being volatile, and that means that the compiler will assume that it'll just assume that it can't assume the value. So if there's a case where it thinks the value is going to be something, it won't optimize based on that. There isn't really many practical applications to doing this, but it's useful for if you want to demonstrate a Stack Overflow or whatever. So another thing in partial evaluation is what's known as constant folding. So if you have a const A in this case, and you're using it in multiple places, it's a little bit like inlining, where you remove constant A, and you replace every instance of constant A with the actual value of it. This has an additional benefit. So like with function B, const A plus 12 has now become 533 plus 12. Earlier, we couldn't evaluate what const A plus 12 is because we didn't necessarily know what const A was. But now that we've replaced const A with its actual value, this is just a math equation which we can do in compile time and save having to do it in runtime. So you can replace that with func B 545. And then finally, code generation it's where you take the result from the rest of the pipeline and you turn it into machine code. There isn't really an awful lot to say about this, but there's three main tasks that take place during code generation. There's instruction selection, where you choose which instructions to run. There's instruction scheduling, where you decide on the order to run the instructions. Instruction scheduling doesn't seem very important, but in reality it very much is, because swapping around instructions, even if it seems like it doesn't really change much functionality-wise, can have a huge performance impacts. And then there's register allocation, where you decide which registers hold which variables, etc. A lot of these things will be decided in the optimization phase, and code generation just kind of acts upon those determinations. So this is a very simplified compiler pipeline. This is probably what an old school C compiler might have looked like. Modern compilers look quite a bit different. So there's what's called intermediate representation. A more modern C compiler, like LLVM, will use intermediate representation as kind of a bridge between a syntax tree and the machine code. And optimizations are run over and over on the intermediate representation to make it more and more efficient. Intermediate representation exists in most languages, and it has different names. Like in C#, it's intermediate language. In Java, it's bytecode, etc. So C# would probably look a bit like this, where the intermediate representation is then passed into a just-in-time compiler. The optimizations happen in the just-in-time compiler, and then that gets sent to code generation. One thing I think a lot of people don't realize about C# is that by default it's just-in-time compilation. So whilst it does spit out a .exe file, it's not a portable executable unless you specify that you want a portable executable from it. So there's kind of a wall between compile time and runtime, where everything intermediate representation and before is compile time. In the case of C#, it's referred to as intermediate language, but it's literally the same thing, and for consistency I've called it the same thing. And then in runtime, just-in-time compilation takes place. As the name suggests, it's just in time, it happens as the program is running. This has some potential benefits in that there are often optimizations that you can only really determine are possible during runtime, and through just-in-time compilation you can perform those optimizations where you otherwise wouldn't have been able to had you done it during compile time. And then an interpreted language like Java would look like this, where you still have lexeme parsing semantic analysis, and you still have intermediate representation, although in Java it's referred to as bytecode. That bytecode or intermediate representation is passed into a virtual machine. In the case of Java, it's known as JVM. The virtual machine has two choices. It can send the intermediate representation into the interpreter or into code generation, and optimization takes place in between going from the virtual machine into code generation, which is why I've kind of got the arrow between the two things. Again, the benefit of using an interpreter is you can have optimizations which you otherwise wouldn't be able to have if you evaluated everything during runtime, or during compile time even. So the interpreter, whilst slower in general than compiled code, can sometimes be faster if there are optimizations that can take place, which would be difficult to implement in a compiled program. I did consider making every diagram like this, but I didn't want to get stabbed during my talk, so I just put this here. So formal grammar. We talked about briefly abstract syntax trees in passing. A grammar is just a way to define that formal structure to create that syntax tree. So remember that lexing takes characters and turns them into tokens. Parsing takes tokens and turns them into syntax trees. Parsing uses a formal grammar to turn an array of lexemes into a syntax tree. So let's take the example again, var a equals var b plus 100. Let's not use a proper formalized grammar yet, but if we were to try and define some rules to try and turn this string of lexemes into that syntax tree, we could maybe say an assignment is an integer plus an equals plus an expression, and an expression is an integer plus a plus an integer. You can kind of see here the var a plus 100 matches the expression. And so you'd be able to replace that with an expression. And then that, then this matches the grammar for a assignment. And so you can replace it with an assignment. But obviously this is very kind of, it's very specific to this case. If you wanted to make it more generalized, it would probably look a little more like this, where we have value, which could be any primitive data type. We have a list of operations, an expression is just a value, operation is a value, an assignment is a value equals a value. It just, I forgot to mention, integer strings, etc., also include variables that hold that data type. So var a, if it holds an integer, would be classed as an integer in the grammar. So if you wanted to turn this into the form which most formal grammars are defined in, known as BNF, it would look like this, which is very similar to what I've just shown. I didn't want to go straight into BNF because some people find that intimidating. So I kind of wanted to go from, like, this is how we would logically think about the rules, and then that's what it looks like in BNF. And another thing to note is that there's an epsilon pipe expression. Epsilon just means nothing. So epsilon is null. It means a value. A value could be nothing. So the cases where you'd want that is like with expression, if you had value, operation, value, but the operation was a unary operation, like a plus plus, it only works on one value, that would still match I++ would still match the expression grammar, because value can be nothing. The second value can just be empty. So, as kind of a more practical example, this is the formal grammar for JSON, and on the side we've got a little bit of JSON, which we're going to try and go almost by hand and try and evaluate using the formal grammar. So we have the string literals apple and apple2, which are values. We replace them with values. Then that fits the pair grammar, string literal colon value. So we can replace those with pairs. Then pair matches pair t-pairs. T-pairs can be nothing. So this matches pair t-pair, where t-pair is equal to epsilon. So we can replace that with pairs. And then pairs matches pairs question mark. So we can replace it with that, and then replace that with object, because object is a pairs question mark between curly brackets. Then, sorry? Oh, okay. So values. Yeah, so objects as a type of value, we can turn that into values and then use the values rules to turn that into a values question mark, which then we can turn into an array, and then we have a pair of pairs, and then we can turn that into, ultimately, an object. That's kind of how you would evaluate, using a formal grammar, JSON into the resulting object. And in reality, you'd have a syntax tree which looks a little bit like this, but it would go a little further. So you'd have object, pair, question mark, pairs, and then the actual things that match towards the end. Those are known as the terminals. So every intermediate step is known as a non-terminal. And then every step at the end is known as a terminal. And if a terminal is nullable, then everything above that is also nullable. I did want to go into parsing, but I didn't unfortunately have time to put that in. Turns out half an hour is a lot less time than I thought it was. But yeah, that's relevant if you want to write a parser. Unfortunately, I had to cut that bit out. So the interesting bit, supply chain attacks. The actual bit relates to cybersecurity here. So compilers are compiled by compilers. You have to use a compiler to make a compiler most of the time. It's kind of like you have to bootstrap a compiler using a different compiler. And compiler modifications can easily propagate. So there was a paper by Ken Thompson in 1984 on Reflections on Trusting Trust, where you can modify a C compilation rules to add new rules to them. And when you compile a new compiler, you can write those rules such that any new compiler you compile with the compiler you brought the new rules into, like the derivative compiler will inherit those rules as well. So, for example, if you wanted to add a \v for a vertical tab, you could add a bit to return the ASCII value of a vertical tab, and now you've got a \v vertical tab in C. But this can be used kind of maliciously as well, where during compile time, you can try and match patterns which you want to replace with some buggy code or some malicious code of some kind, which means that any derivative compiler you end up with will then inject malicious code into whatever source code it compiles. And obviously this, you can't even solve this through analyzing source code, because it's not the source code that's the issue. The malicious code is added during compilation, which is very difficult to detect. It's a Trojan horse attack. One remediation was discussed in a dissertation by David A. Wheeler in 2009. It's known as diverse double compilation, where you use a trusted compiler to verify the output of the compiler under test through multiple stages of compilation. There is a slight drawback with this in that whilst DDC doesn't require the two compilers to output the same thing, for DDC to work, the compilers need to be derivatives of each other. So DDC works where you have a trusted compiler and you have a new compiler that's a derivative of that compiler. And you want to verify that that derivative isn't injecting malicious code into whatever it is that you're compiling. This kind of thing has happened before. In 2015, Visual Studio started injecting telemetry through the C and C++ compilers. So, without realizing it, code that you compiled using a Visual Studio compiler would inject telemetry that would go back to Microsoft in the source code that you wrote without you actually putting telemetry in there. So, it is a thing that genuinely happens and is obviously a concern. And if big companies like Microsoft are willing to do it, it's something that we need to kind of be aware of. Kind of the whole point of this talk is by understanding how compilation works, you understand these potential attack vectors, which otherwise are kind of abstract and difficult to detect. I don't think many people would have thought about a compiler being the source of a vulnerability or being a source of injecting malicious code into otherwise perfectly fine source code. So anyways, that's the end. Are there any questions?